Writing formulas for ionic compounds. The first thing we do is we write the symbol for the metal cation. The metal always comes first. And we include its charge, followed by the symbol for the nonmetal ion with its charge. When we start doing formulas, we first have to do a little bit of work. You have to write some scribbling down. Later, you might be able to just put them together without writing anything down. But if this is new to you or it didn't go well last time, write it down. It really is better. The symbol for each ion with their charges. Then we're going to adjust the subscripts. We're going to put subscripts on each cation and anion so that overall the charges balance out. Because in a compound, all the charges add up to 0. It's not charged overall. And then we're going to check to make sure that we did it right. We're going to check the sum of the charges. I think I'm going to stick an example in here and just make something up. No, I don't feel like making anything up. I'm not going to. Sorry. Summarizing ionic compounds, I really just don't remember where these are going. It just makes it so fun and scary. Remember that ionic compounds always contain a positive and a negative. The first element is usually a metal, except ammonium. If that's first, still an ionic compound. The positive always goes first. Why? Because that's it. They decided. You address a formal invitation to Mr. and Mrs. so-and-so, right? It's not Mrs. and Mr., just because that's how everybody does it. So the metal always goes first. The cation always goes first. I think of the metals as being masculine and the non-metals as being non-masculine or feminine. So guy, girl, metal, non-metal. Kind of already stated this part with them adding up to 0. Important that the formula be the smallest whole number ratio. So we don't want, Na2Cl2. We want the smallest ratio. Because everything should have one right formula, not multiple different options for the formulas. Okay, here's examples. Write the formula for the ionic compound that forms between magnesium and chlorine. First step is write the element symbols and then the charges for the ions. So magnesium is what symbol? Mg. And what charge does a magnesium ion have? It's a 2, positive 2. Metals form positive ions, non-metals negative ions. And then we have chlorine, is Cl. And what is the charge on the chlorine? -1. We look at the periodic table, and the halogens are 0, and we go backwards, -1, -2, -3. So chlorine is -1. So we got the formulas with the charges, and then we have to figure out how are we going to stick these together, how many of each, so that when we push them together, they add up to 0. First thing to look is, are the charges the same? +2 and, no, that's not -2. If you've got +2 and -2, just shove them together, and you're done. These are different. So the thinking way is to think about this and say, well, I've got a +2, and then I must need 2 of those -1s, and then they'll add up. And so you write down MgCl2. So that's great. Some people need a little more illustration. So if I put these two together right now, they're not going to add up to 0. I need more of these because the total at the bottom here, I've got 2 plus and right now I've got 1 minus, and I need them to be the same. So if I draw another one of these, then I've got 2 minus and 2 plus, and then I'm good. There's many ways of thinking about this. Whatever way works for you and gets the right answer is absolutely fine. So that's another way. And then there's the crisscross, which is usually a student's favorite. You can get in trouble with the crisscross. I'm just having trouble with my 2 there. So crisscross, you look and you make sure that these are not the same number. And if they're not the same number, this becomes the subscript over here, and that becomes the subscript over there. This is an unwritten 1. It becomes an unwritten 1 down there. This is a 2, and that becomes a 2, and we get MgCl2. So let's do aluminum and sulfur. Aluminum is Al. What charge does an aluminum ion have? +3. Because it's in group 3, and it's a metal, it's +3. How about sulfur? -2. So we write 2 minus. Because it's over 2, we go -1, -2. There we go, sulfur on the periodic table. And some of you can look at that and say, oh, well, 6 is the least common multiple of 2 and 3, and we'll just do that. And other people are like, huh? You can do the crisscross thing. Here we've got +3 and -2. They're not the same number. We could do the crisscross thing. We end up with Al2S3.
How does it get you in trouble?
It can get you in trouble if you have something like tin 4 and sulfide. Those 2 numbers are not the same, but when you crisscross, you get SN2S4, which is not the smallest ratio. It should be SNS2. Yeah, as long as you check, you need this to be the lowest ratio. 2 to 4 is not the lowest ratio, so you'd have to reduce that. 1 to 2 is the lowest ratio. So don't just crisscross, without thinking at all, because it works most of the time without any trouble. But I just need to caution you that it does not always work. So the more picture way is, because this is a fun one to do it with. So here we've got +3 and we've got -2, and they're not the same. We need more of these, so I'll draw another one of those in. And now I've got -4, and we're thinking, oh great, now I've got too many of those. I need another one of these. And now I've got +6, and now I went off the other way, and is this ever going to end? And then you go to minus over here. Now I've got -6, and you're like, phew, I thought that was never going to get. And then you count up, I've got 2 of these, and I've got 3 of those, and there I've got my result. Some people just need pictures. And if it's still not clear to you, please ask me, and I'll show you. I've got other ways. There's bowling balls in boxes on teeter-totters. There's all kinds of things. So I'm sure someone will ask me just because they're wondering how I can get bowling balls in boxes on teeter-totters to relate to ionic equations or formulas. But so these 2 guys, what's the formula for those? So it's going to be FEN. +3 minus 3. We don't have to do anything, just shove them together. Now, just very, very important. Didn't mean to do that. Here, the ion by itself, we write the charge. In the ionic compound, we do not write the charges. Do not write the charges in the ionic compound. When the ion's by itself, you write the charges. Okay? The representative or main group elements, we can predict charges on the periodic table. And those representative elements, the main group elements, they only form 1 ion. So that's nice. Group 2A, we know all of them form +2 ions. Awesome. The transition metals are the ones in the sunk down part of the periodic table, and those guys are squirrely. A lot of them form 2 or even more different ions. Iron makes a +2 and a +3. And you can't tell from the periodic table which one you're dealing with. Okay, we're getting to that eventually. Yeah, there we go. Okay. There are compounds that have common names. Water is a common name for H2O, but most compounds, we use their systematic names. And in order to use the systematic names, we have to first identify what kind of a compound are we dealing with. So we already talked about the difference between ionic compounds and molecular compounds. They have different sets of rules for naming, just like different countries have different patterns for how they name their children. My ancestors came from Sweden, and when my kids did the family tree thing, you go back a little ways, and the last name changes every generation. Because if your dad's name is John and you're his son, then your last name is now Johnson. And if you are Peter Johnson, then your son is Michael Peterson. And then his son is so-and-so Michelson. And it changes. And then the girls, they instead of putting son, it's daughter. So you could be Carl's daughter or Olaf's daughter. Very interesting, right? Different than what we use in the United States, where the child takes the last name of the father. So you have to know what country you're dealing with. They don't do it that way in Sweden anymore because it got really annoying, I think, but they used to. But with the elements and the compounds, we need to know what group so that we can apply the correct system of naming. So we already learned to identify ionic compounds. We're looking for a metal or NH4. The metals, the ionic compounds, the books really like to divide them into two different types. I think it's a little silly, but there it is. The first type is a metal whose charge is always the same, and the second is one of those squirrely transition metals where they can have different charges. I prefer to think of just naming the ions based on the sorts of things that they do. These elements form ions that always have the same charge. And most of these are groups 1A, 2A, and 3A. So these guys, and I'll be repeating this over and over again, groups 1A, 2A, and 3A. They form ions that are predictable based on the group number. Then there are a couple extra guys. Scandium is in here. We were not going to run into scandium very much. Where is he even? Way over there by calcium. Scandium's just annoying. Scandium's +3. The two that are important here, zinc and silver. Zinc's +2, silver is +1. And I'll show you how you can remember that off the periodic table as soon as I see if there's a periodic table coming up. No, there isn't. I desperately need a periodic table. There's one back here somewhere. There it is. Okay, so this was for something else, but I'm going to use it for my purposes. So here we have group 1A, +1 ions. Group 2A, +2 ions. Group 3A, +3 ions. Mostly that's going to be aluminum. You're not going to run into the other three down there, gallium, indium, and I forget what TL is. We're definitely not going to run into him. Now, the two that you have to just remember are these two guys, zinc and silver. This is how I do it. Doesn't it look like we're going down the stairs here? Here were 3. This is 3 because it's group 3. And then we go down 1. This is 2. We go 3, 2, 1. Zinc is +2. Silver's +1. Those elements, group 1A, 2A, 3A, zinc and silver, always form the same charged ion. Okay, let's go back. So that's those guys. Again, there's scandium in there, but I'm going to ignore him. The others, the other metals can form more than one ion depending on the compound. So here we've got chromium can be +2 or +3. Iron can be +2 or +3. A lot of them with the 2 and 3s. Copper +1 +2. Lead is fun, +2 and +4. Skips +3. There's no predicting this from the periodic table. And then mercury is extra fun. Mercury forms 2 different ions, but one of them is, I guess you could call it polyatomic. There's mercury with a 2+ charge, and then there's this one. It's a diatomic ion together with a 2+ charge. That one's just weird. So if you're really wanting to get an A in the class, then you should remember that guy. If something less than an A but still very nice, like a B, is fine, then that's one of those things that you could just kind of skim over. It'll come up once in a while. These guys have different charges, and so their name has to tell us what the charge is. So we use Roman numerals. So the name of Cr2+ is chromium 2. The name of chromium 3+ is chromium 3. So we specify the charge using Roman numerals. And just in case you forgot, this IV, that's 1 before 5. V is 5. 1 before 5 is 4. And that's about as high as they generally go. This is an older system of naming that you'll occasionally see. I find it very annoying. This is the current system that everybody uses. You have to learn this one. That one, you'll still find things labeled that way. They use ic and us for the lower and higher charge, but it doesn't specify what it is. And so I will avoid that older system because I don't like it. Oh, see here? There it is right there. Okay. I always forget what's coming up. Mrs. K's tricks. Okay, so group 1A, group 2A, they form ions with a charge equal to the group number. And then we get this triangle. The triangle is also predictable. This is group 3. These guys are 3+. Group 2, zinc. Actually cadmium 2, but your book didn't mention that. And then silver. And so there's 3, 2, and 1. If it's not in the triangle or group 1A, 2A, you have to use a Roman numeral when you name it. So the anions, I guess I didn't specifically say, the name of the cation is just the element name, unless it's one of that large group that needs the Roman numeral. The anions are the nonmetals. And like I said, the nonmetals are more like women, and the metals are like men. And traditionally, when a man and a woman get married, who changes her last name? The woman, right? So when a metal and a nonmetal form a compound, the metal doesn't change his name, but the nonmetal changes the ending of her name. And so we take the element name and we just change the ending to "ide." So fluorine becomes fluoride. And remember, there's no flour in fluorine. It's UO. Chlorine, chloride, sulfur, sulfide, etc.
Every discussion you had with your husband, did you ever consider keeping the last name?
We learned how to name the 2 different ions. When we put them together, we just name the guy first and then the girl. The metal first, the cation, and then the nonmetal. So a binary compound is 2 elements. Binary means 2. And so here we're going to have a metal cation, and we're going to have a metal nonmetal anion. It's just going to be a monatomic ion. It'll be an element with its name ending changed to "ide." So for something like KCl, we got potassium. Potassium is in group 1, doesn't need a Roman numeral. And then we name the anion chlorine. She changes her name to chloride, and we get potassium chloride. Here we got calcium and oxygen. Calcium is in group 2A, doesn't need a Roman numeral. And if you have a hard time remembering, the way I think of it is this: we're trying to be concise. We don't want to write a lot of extra stuff. Calcium doesn't need a Roman numeral because we've got the periodic table. So we don't need to write the Roman numeral. We're not going to do it unless we need to. So calcium is just calcium. And then oxygen is a nonmetal. We just change the ending to oxide, calcium oxide. Most compounds have 2 names. And so for these binary ionic, there's 1 name for the metal and 1 name for the nonmetal. So let's name these guys. BaF2. Barium is the first element. The first ion is barium. Does he need a Roman numeral? No. And then fluorine, we change the ending to fluoride. Remember, there's no flower in fluoride. No flower. People do that all the time. Anyway, K2S. What's K? Potassium. Does it need a Roman numeral? No. And S is sulfur becomes sulfide. All these guys end in "ide." Any questions? And then your book makes this second group of compounds with metals that have more than one kind of cation. It's the same idea. We have the name of the metal, but now we need a Roman numeral, and we have the name of the nonmetal. How do we figure out what the charge is, though? Because we don't know from the periodic table. We have to figure it out. Inference from the sum of the charges of the nonmetal. So we have to look at the formula and figure out what must the charge on that one be. So CrBr3. So we look at, this is chromium, and we find chromium on the periodic table. Does it need a Roman numeral? Yeah, it's not in group 1A, 2A, or the triangle. So it needs a Roman numeral. We have to figure out what the charge is. Well, the total cation charge and the total anion charge have to add up to 0. Yeah, this is all written out, but I'm just not liking it. So I'm going to do it on the side here. So we've got chromium and we've got bromine. What is the charge on the bromine ion? -1. And we've got 3 of those, right? There's 3 of them. So the total charge, we know there's 3 because of the little 3 there. So we've got -3 charge over here. That means that we must have +3 charge over there. And we look at the formula, there's only 1 chromium ion. So it gets the whole charge. Must be 3+. So then the name becomes chromium 3. When we write this, there's no space between the element name and the parentheses. So chromium 3 space bromide. And these are not proper names. We don't generally capitalize them. Questions? So let's name these guys. MnCl2. So Mn is the symbol for what element? Manganese. My favorite made-up element is manganesium. It's like, well, we'll hedge our bets and put the 2 together. Does manganese need a Roman numeral? Yes. So what works a lot, or works for many people, is just put the parentheses in there to save some space, and then Cl is what? Chloride. Now we have to figure out the charge. What's the charge on the chloride? -1. And there's 2 of those. right? There's 2 of these, so the total charge on the anions is -2, and there's 1 cation, it must be +2, right? +2, so Roman numeral 2. PbO2. Pb is lead. Does lead need a Roman numeral? It does. Oh, that's probably a little big. Where is lead? It's in group 4A, right? Is it a transition metal? Not really. It's not a transition metal, but it's not in group 1A, 2A, 3A, or the triangle. It's over there in no man's land. It needs a Roman numeral. So it's not just the transition metals. I'm going to leave a space, and the name of the oxygen ion is oxide. So oxide has what charge? -2. There are 2 of those. That adds up to -4. Here I've got how many lead ions? 1. It must have a charge of 4+. Any questions? Can you do this in your head without writing this stuff down? Sure, once you get good at it. So if you're getting the answer right every time, go right ahead. But if you're getting the answer wrong, then start writing things down until it's more automatic. And this is a fun one. Hg is what element? Mercury. Does mercury need a Roman numeral? Yes, it does. Save a space. S is sulfide. Okay, so we have sulfide with what charge? -2. And then we've got mercury, and there's 2 of them. And so here we've got -2, and over here we must have +2. So what should it be? Each of these would be +1, right? So that's mercury 1. Now mercury 1 is not written like this. It's Hg2, 2+. It's that weird guy I told you about. But it worked out just fine here when we did it like that. Mercury 1 sulfide. Any questions? Then we have ionic compounds with polyatomic ions. Follows the same pattern. You name the cation and you name the anion. It's just that now the anion is more complicated and basically has a name that you have to memorize. I already made you memorize a whole bunch of them. So if we look at something like this, NaNO2. Nomenclature, which is the system of naming things, is not a place to be creative. Okay? Students get really creative and they tell me this is sodium nitrogen dioxide. No, it isn't. First element is sodium. Sodium is a metal. This is an ionic compound. All the ionic compounds we're going to name are going to have 2 ions. 1 cation, 1 anion. So the metal is an ion by itself. Everything else stays together. So we name the cation is sodium, and the anion is NO2 minus, and its name is nitrite, and so the name of the compound is sodium nitrite. So here are some common polyatomic ions. Hopefully these look pretty familiar to you. Some of them, like HSO4 minus, has two possibilities. We can call it bisulfate or hydrogen sulfate. I prefer hydrogen sulfate because it's more descriptive, but we should probably recognize both. Carbonate does the same thing, hydrogen carbonate or bicarbonate. This is carbonate, and if we add a hydrogen atom to it, a hydrogen ion, excuse me, then we get hydrogen carbonate. So, gotta memorize those guys. Most of those are oxyanions. Let's go back and look at that. Most of these have oxygen in them. Now this one doesn't count as an oxyanion because the oxygen comes first. He's kind of special. Ammonium's not an oxyanion. Cyanide isn't. But most of these guys, there's some nonmetal or occasionally metals with oxygen. There are series, meaning there are two similar polyatomic ions, and the only difference is the number of oxygens. There's NO2 minus and NO3 minus. The number of nitrogens is the same, the charge is the same. All that's different is the number of oxygens, and so the names are really, really similar. NO3 is nitrate, and this is nitrite. Ite is like light. It's the light version. Well, that doesn't work. It's on the next slide anyway, so we'll get to it. SO42 minus is sulfate. The light version is sulfite. It's just got one less oxygen than the regular sulfate. The halogens form larger series, 4. And so here we have chlorate and chlorite, and then hypochlorite. Where does a hypodermic needle go? Under your skin. Hypo means less than or below. So hypochlorite is one less than chlorite. If someone is hyper, do they have more energy or less energy? More. Per means more. So perchlorate has one more oxygen than chlorate. So if there's a definite pattern here, if you remember the 8, memorize this one. Per is one more, ite is the light version, hypo is one below the light version. Bromine does the same thing. Just use the main part of bromine's name in here. Iodine does the same thing. Per iodate, iodate, iodite, hypoiodite. So, more of Mrs. K's tricks. Memorize the 8s and the pattern. So hyper has more. Memorize that one. This is the light version. One less oxygen than the regular. Coors Light is a third less calories than the regular Coors or whatever. Actually, it's Bud, isn't it? Bud Light. Hypo means below, one less. And just know, this is upside down of how it's shown in the text. Because I think more is higher. And so I like it this way. And I made the slides, so. Any questions about those guys? So let's name these. FeClO4 2. It hasn't been mentioned in the slides yet. What are these parentheses doing? These parentheses are like the shrink wrap around this bundle pack. You buy something at Costco and you can't just buy one, right? They're bundled together. You got to buy 2. Or in this case, it might be a game system with 4 games and it's all bundled together. You say, but I don't want the extra games. Well, you have to take them. They're together. It's a polyatomic ion. Here we have 2 of them. So we put parentheses around the outside and we have the ClO4 inside. And just to show you maybe an example of why we don't do it without the parentheses, if we went like this, that looks a lot like 42 oxygens, which is kind of ridiculous. Or if we did it like this, Cl2O8, then it becomes really difficult to recognize that that's perchlorate ion. So we put parentheses around it and the number on the outside. So here's the metal. We name him. Everything else gets named as a unit. So don't tell me chlorine tetraoxide. I will laugh. So Fe is iron. Does it need a Roman numeral? Yes, it does. Leave space. ClO4 is what? Perchlorate. It's got an extra oxygen. Perchlorate. And then let's think about this. What's the charge on the perchlorate ion? -1. We have 2 of these. So 2 times that charge is -2. There's 1 iron, so its charge must be +2. Iron 2 perchlorate. We have to include the Roman numeral because there's also iron 3 perchlorate that has 3 perchlorate ions. And we need to be able to tell from the name what the formula is. Here we've got LiCN. The lithium is the metal. He's by himself. Everything else named together. Already gave away the element name, lithium. Does lithium need a Roman numeral? Nope. Cn is what? Cyanide. Just got to memorize that. Na2SO3. The sodium and what's left? Does sodium need a Roman numeral? Nope. It's also in group 1. What's the name of this guy? Sulfite. Sulfate is SO4. So spelling matters, right? If this I is an A, or if I can't tell the difference, then it's wrong. Any questions? Some ionic compounds are hydrated. When a person is well hydrated, their body has plenty of what? Water. So an ionic compound that's a hydrate has water molecules associated with it. Now this doesn't mean that it's wet, but that there's a particular number of water molecules that are associated within the crystalline structure. An example is Epsom salts. That's the common name for magnesium sulfate heptahydrate. When we name these, we name the ionic compound first. There's a dot here that doesn't really imply multiplication or anything. It's just a separating dot. These two are together and yet. And then there's 7 waters. So the 7, the prefix meaning 7 is hepta, heptahydrate, magnesium sulfate heptahydrate. This guy, COCl2, cobalt. Cobalt is not group 1A, 2A, or the triangle. Needs a Roman numeral. We figure out the charge must be 2 because of the charge on the 2 chlorines. Each of them is -1. Total of -2 here. That one must be +2. Cobalt 2 chloride, 6 hexahydrate. These prefixes will get used for many things, so you need to learn these guys. Hemi is one that we don't use except when we're naming hydrates, and that may seem weird. How can you have half of a water molecule? Well, actually there's one water molecule between 2 of these, but the convention is you use the formula for the ionic compound and then the dot and however many there are per formula unit. Mono, di, tri. Tetra might be a little unfamiliar. Penta, like a pentagon, hexagon. Hepta is weird, that's 7, and then you should be okay with octagon. Octa, meaning 8. So let's name these guys. CaSO4 dot 1/2 H2O. Calcium sulfate. And what do we do with the Hef? Hemihydrate. Hemihydrate. Hemi and semi, kind of alike. No Roman numeral because calcium is in group 2A, doesn't need one. What's this guy? Barium chloride. Hexahydrate. So these compounds have 3 names. Sometimes people go by 3 names too. Let's name this guy, not name this, write the formula. Copper 2 sulfate hexahydrate. Writing the formulas, we write the names. No. Right? We have the name. We're going to write the formula for each of the ions, maybe off to the side. Copper 2, copper is Cu, and the 2 means what? It's the charge. It is not the number of coppers in the formula. That's a common mistake. Sulfate is what? SO4, 2 minus. You have to memorize that. So we've got the cation, the anion. We look at their charges. They're the same but opposite in sign, so we just smash them together. CuSO4. Hexa means 6, so we put a dot here. 6 H2O. Any questions? Yes?
Would it bother you if you put sulfate in parentheses?
Would it bother me if you put sulfate in parentheses? It would just look weird. It would look weird because there's no subscript on the outside. If we needed 2 of them, then we have to use parentheses. So, we're trying to be concise and not write any more than we have to. And the result is the names and the formulas should come out exactly the same, no matter who puts them together. If you're coming up with the right name, it's going to be the same name, which is something that just really appeals to me. I like it when there's one right answer instead of all these opinions. Any other questions?